Hello and welcome to another day of geometry. We get to build off our idea of the tangent ratio that was developed in the previous video. And so for this warm-up problem, what I'm going to ask that you do is you solve for the missing variables in each of the triangles, which should not be too overwhelming if you've been paying attention and following along with us back at home. So I'm going to pause the video and allow you time to go through and work and draw these triangles and really edify those skills of the tangent ratio, and we'll see what we come up with as soon as I come back on the video. Alright, let's see how we did. As a reminder, what we established yesterday, we talked about this thing called slope ratio. And slope ratio is the ratio of the opposite leg to the adjacent leg given a particular slope angle. And so we call that ratio the tangent ratio. So we use this equation called tangent. The tangent of an angle is the opposite leg divided by the adjacent leg. So in the first problem, I identified this 28 degrees down here. The side length across from that is not the hypotenuse, that is the opposite leg. The side length that is next to it is the adjacent leg. So you need to identify those values. Then I set up this ratio over here, which is our tangent ratio. I said the tangent of 28 degrees using this up above is equal to z, the opposite leg, divided by 14, which was the adjacent leg. And then from that point I cross multiplied and I solved. Remember, in your calculator you should type in tan 28 and then you just hit enter. 14 times tan 28 and should give you 7.44. As you look at number 6, I ended up getting 1.16. You could have used either 20 degrees or 70 degrees. It does not matter what your reference angle is. It will just change your fraction on the right in that regard. On number 7, hopefully you got 133.38. You can see my work there. On number 8, you actually don't have to use the tangent theorem or the tangent ratio in order to solve. In this case, you just have to use Pythagorean theorem, which, remember, because I have two sides of a right triangle, I can do a squared plus b squared equals c squared. And when I got that for c, I ended up getting roughly 119.67, or the square root of 14,321. On number 9 down here, notice that those are two 45-degree angles, meaning it's an isosceles triangle. Therefore, the ratio of the two legs should be the same because the tangent of 45 degrees is 1. So that means x is 12.25. And on the last problem I did the tangent of 15 degrees equals w over 47, cross multiplied, typed that in, and I got 12.59. If this is something that you're struggling with still, people, please reach out. This is a very important concept, an essential skill that is not going to go away. So if you need help, please swing by office hours and we can work on it. So today we start a new section in Chapter 4, which is Lesson 4.2.1, entitled Using an Area Model. And so what we're going to do is we're going to study probability and see what is the probability that a particular event is going to happen. And we're going to use a term called sample space as what we have defined right here. In the homework, you've practiced probabilities beforehand, but what we're going to do today is use a tool to help us analyze more complicated situations and use something called an area model. So problem 453, I would encourage you to write down this diagram. We're going to do that here in a little bit. This is called the sample space right here. It says, can you bend your thumb backwards in the middle joint to make an angle, like at the right, or does your thumb remain straight? What about rolling your tongue? And so it says, assume that half the U.S. population can bend their thumbs backwards and that half can roll their tongues. Also assume these genes are independent, meaning that having one doesn't affect one or the other. Then the sample space below of these genetic traits can be organized in a table. So this right here, this thing is called a sample space. And so this is a list of all of the possible outcomes for each of the situations. So for example, around here we have yes, you can roll your tongue, or no. And up here is yes, you can bend your thumb backwards, and no, you can't. So this outcome in this box right here would be a person who can do both. Yes, yes. This would be yes, you can roll your tongue, but no, you can't bend your thumb backwards. This is no, you can't roll your tongue, but yes, you can bend your thumb backwards, and this would be no to each of them. So that shows me all of the possible outcomes. I have 4 possible outcomes if I were to pick a person from the US that has both special traits. That is, what is the chance that he or she can roll his or her tongue and bend his or her thumb backwards? So the first question in part B then says, according to this table, what's the probability the person only has, excuse me, I got ahead of myself. What is the chance that he or she can roll her tongue and bend his or her thumb back? So we're really answering, hey, what is the probability that we get this box? And the way that we do that is using an area model. This is called an area model. And in order to determine the probability of this box, we take the likelihood that this event occurs and multiply it with the likelihood that that event occurs. So that's going to be 1/2 times 1/2, which is 1/4. So the probability of getting a yes, yes is 1 out of 4 according to our area model. So what's the chance that he or she can do both? Then, well, that'd be 1 out of 4, or roughly a 25% chance of happening. Now, in part B, according to this table, what's the probability that a random person has only one of these special traits? Well, one of those special traits would be this conclusion here, no yes, or yes no. Now the probability of this box is also 1/4, as it would be 1/2 times 1/2, and this would also be 1/4. So what is the probability? Well, that'd be adding these two situations together, and 1/4 plus 1/4 is 1/2. So if I have 2 different outcomes that could take place, I add those probabilities together, that is 1/2, or it's roughly a 50% chance that that is going to take place. The probability that a random person has one of these special traits. So this table is useful because every cell is equally likely, therefore each outcome has a 1/4 probability. So it says, though, however, this table assumes that half the U.S. population can bend their thumb, but in reality, only about 1/4 of the U.S. population can bend their thumbs, and 3/4 cannot. And also, about 7/10 of the population can roll your tongues. Can this table be adjusted to represent these percentages? Yes, it can, and that's what we're going to dive into as we go into the next problem. So one way to represent the sample space that has outcomes that are not equally likely, so for example 1/2 and 1/2, is what we're going to use called a probability area model. There's an area model that uses a large square with an area of 1, and the square is subdivided into smaller pieces to represent all of the possible outcomes in the sample space. The area of each outcome is the probability that it will occur. For example, if 1/4 of the U.S. can bend their thumb backwards, then we create a column representing 1/4 of that area. So how should the diagram be altered to show that 7/10 of the U.S. can roll their tongue? Well, the way that we would create that diagram then is we would have a horizontal line going across here, and this would say yes over here above, and that would be a 7/10 chance that would happen, and that would mean that there's a 3/10 chance that we would not be able to. And so you can see there's 4 separate quadrants now, but they're not all equally likely. You're not all going to have the same possible outcome in order for that to happen. And I would encourage you to draw this diagram right now if you have not done so already. And we're going to go on to part B. It says the relative probability for different outcomes are represented by the areas of the regions. For example, the portion of the probability area model representing people with both special traits is represented in this box right here. Yes, yes. Okay, this is somebody who would have both special traits in this box. Now, what is the area of that rectangle? Well, the area of this rectangle, again, is going to be found by multiplying the height and the width, or the base and the height of that, which would be 1/4 times 7/10. And in multiplying those together, I'm going to get 7 out of 40. So the probability that we would get a yes, yes, somebody can roll their tongue and bend their thumb backwards is 7 out of 40, or approximately 17.5%. So the area of the shaded in region represents the probability that that event will occur. And so we find that area by multiplying the two probabilities together. So question C says, what's the probability that a randomly selected person can roll his tongue or roll their tongue but not bend it backwards? And so in order to do that, what I'm going to do is I'm going to actually be multiplying and finding this probability right here. Okay, and I'm going to be multiplying that with the 3/4, so that would be yes, roll the tongue, but no, cannot bend it backwards. So in order to determine the probability of that shaded in region, what I need to now do then is I need to multiply 3/4 times 7/10, and in doing so I'm going to get 21 out of 40, which is approximately 52.5%. So the probability that somebody can bend their thumb, not bend their thumb, but can roll their tongue is about 52.5%. So we use this thing called a probability area model with the relative probabilities in order to help us find out, hey, what's the probability that something will happen? So now we're going to kind of pull it all together. It says you and your best friend may not only look different, but you might also have different types of blood. For instance, members of the American Navajo population can be classified in two groups. 73% of the Navajo has type O blood, while 27% has type A blood. And so it says, suppose you select two Navajo individuals at random. What is the probability that both individuals have type A blood? This time, drawing an area model that is exactly to scale would be challenging, like in the last problem. So a probability area model like the one shown above is still useful, but from here on out, and what we're going to do is draw like what they have up above, is we're not going to worry about drawing it perfectly to scale, 73 out of 100 for one portion and 27 out of 100. We're just going to draw it as a normal area model like we've been doing in the past for multiplying and other things, but we're going to understand that completing this area model in terms of filling out its associated probabilities, for example, finding the area here that a person would have type O, so this would be person 1 and person 2 both have type O. I would find this probability by multiplying together 0.73, which is 73 out of 100, and 0.73 into my calculator, and when I do that I get 0.5329. So that's 0.5329, which then as a percent, remember we moved the decimal point over and it's 53.29% chance of happening. This box over here of person 1 having type A and person 2 having type O, the area of this box right here represents that probability of having type A for person 1, type O for person 2, and the probability of that taking place would be 0.27 times 0.73. And in multiplying those together, you're going to end up getting 19.71%. And that's actually going to be the exact same probability as this box would be down here, where person A has type O blood, or the first person rather has type O, and the second person has type A. And in this instance, I'd multiply 0.73 times 0.27, which is going to yield the same outcome, which is a 19.71% chance of happening, where you have that combination. And then lastly, this instance here where person 1 and person 2 both would have type A blood, that probability would be found by taking 0.27 and multiplying that with 0.27, the probability of each particular outcome, and when you multiply those together you get 7.29%. So this area model represents all of the different probabilities. What you should note when you add up this probability, this one, and this one, they should all add to 100. Remember, the area of that big rectangle, the whole thing, should add all the way up to 1 or to 100%. So in analyzing this, at the very end, it says what's the probability that two individuals selected at random will have the same blood type? Well, the same blood type is either AA or OO, so adding those two together would give us roughly 60.6% chance that somebody would have the same blood type. So as we end the lesson today, we're actually just going to skip ahead to the math notes. We're going to work a lot more with probability area models and determining outcomes. But as a brief reminder, the textbook and I wanted to come back to this idea of solving quadratic equations. It seems like something completely amiss or far off, but it is an important skill. So remember, when solving a quadratic, it's something that's written in this general form where we have one term that's raised to the second power. And so you can solve that either by factoring in the zero product property, or the method that always works is the quadratic formula. And here's the quadratic formula. And remember, when you solve quadratics, it can give you up to 2 possible solutions. And so we often use a plus or minus sign. So in solving this quadratic equation, this would be a great practice problem for you to make sure that you still understand what's going on. You can use quadratic formula or factoring. For that instance, you should end up with the results of 5 and -2. As always, if you need some extra help, please swing by the office hours. We can talk about that as we move forward. Hope you all are doing well. Stay safe and stay healthy.